Cross-region read replicas and global databases the problem. Global latency and single-region blast RAID-EU are operating under the dangerous delusion that your users will tolerate a 300 milliburst round-trip time just because your data layer is highly available inside US East 1. When a user in Frankfurt or Tokyo hits an endpoint that requires a synchronous database read, their request must traverse oceans, fight speed-of-light physics, and navigate congested transit providers just to fetch a profile record. This cross-continental back-and-forth completely obliterates your front-end's core web vitals, drives up abandonment rates, and tanks your conversion metrics. Worse, relying on a single region means you are one catastrophic AWS networking outage away from total business blackouts. When a core service in your primary region degrades, your entire global user base is cast into darkness. You cannot build a resilient, high-speed international application on top of a geographically localized database footprint. Engineering reasoning the solution requires decouplement of read traffic locality from write traffic synchronization through the implementation of cross-regio, NRead replicas, or fully managed global databases. From a distributed systems perspective, read replication relies on asynchronous physical or logical replication streams. In a standard setup, the primary instance writes to its local storage engine and concurrently ships its write-ahead logs or bin logs across the cloud provider's private fiber backbone to a target instance in a secondary region. Client in Europe, low latency read, and read replica, EU Central 1. Asynchronous replication. Client in US, write request, and primary DB US East 1. This architecture unlocks two critical advantages. Data locality. Read queries are terminated within the closest geographical cloud edge, dropping database network latency from hundreds of milliseconds to single-digit figures. Disaster recovery, DR, RTO, IPO. In a total regional meltdown, the secondary cross-region replica can be detached and promoted to a standalone primary database. This slashes your recovery time objective, RTO, from hours of snapshot restoration to minutes of DNS reconfiguration, and bounds your recovery point objective, RPO, to the replication lag, typically 1 second under nominal conditions. Cost comparison. Managing a cross-region data footprint introduces two specific cost dimensions: compute overhead for the secondary instance and cross-region data transfer, DDO fees. Dotman single-region deployment, cross-region replica deployment, compute, storage 1x primary instance and 6G 2x large, plus storage $740, Mo 1x primary plus 1x replica, DB. M6G.2x large in secondary region, 1,480 AMO data transfer, months per GB. For intra-AZ AMO data traffic, C2s per GB transferred out of the primary region to the replica region. Total. At 500 gigabytes egress, MAMO 7,490 month, the financial T. RAID off. While your infrastructure run rate essentially doubles for the database layer, you are buying insurance against total business operational failure. Compare a $750 monthly premium against the astronomical cost of an 8-hour total blackout during peak trading windows, where loss of revenue, SLA penalties, and engineering overtime can easily breach 6 figures. Actionable fix. Terraform AWS RDS example. Implement a cross-region read replica by referencing your primary database's Amazon resource name, ARN, within a distinct provider block mapped to your T. RGET secondary region, Terraform primary region provider. Provider, AWS. Alias, primary. Region, US East 1. Secondary region provider. Provider, AWS. Alias, secondary. Region, U Central 1. Primary database instance. Resource AWS primary. Provider AWS.primary. Identifier production primary DB. Allocated score 100. Engine parses. Engine Vivation 15.4. Instance.m6g2x large. Username dbadnorner. Password var.db. Skip donas false. Backup retention perit 7. Cross-region read replica. Resource obvious.bdis replica. Provider WS Skinner. Identifier production replica EU. Replicate dos.b.dos.pray must reference the primary ARN. Instance class DBM6G2x large. Match primary instance size for performance parity. Skip Dufnal Sap Mots true. Tags. Environment production. Role cross-region replica. Automated partitioning and horizontal sharding the problem. The monolithic storage wall and query degradation. You cannot continue scaling your primary database vertically forever. As your transactional tables swell past hundreds of millions of rows, you hit a performance wall. Index lookups that once took microseconds mutate into agonizingly slow disk operations because your B trees have grown too massive to fit entirely within the database instance's RAM, the buffer pool. Every single sequence scan or poorly optimized join begins triggering massive I/O operations, pinning your CPU at 100% and choking your entire application thread pool. Vacuuming, optimizing, and backing up a multi-terabyte monolithic table creates intense lock contention, occasionally freezing writes altogether. If your plan to handle next year's user growth is simply upgrading to a larger cloud instance size, you are sprinting toward a hard technical ceiling where your database will collapse under its own gravitational pull, unengineering reasoning when vertical scaling fails. You must distribute data engineering chunks horizontally through partitioning, intra-instance separation, or sharding, cross-instance distribution. Table partitioning, logical split, breaks a gargantuan table down into smaller, highly manageable underlying child tables based on a partition key, e.g., date ranges or tenant IDs. The query planner uses a technique called partition pruning to completely ignore irrelevant child tables. If a query looks for data from June 2026, the database engine executes an index scan only on the June 2026 child partition, keeping the required B tree indexes small, hyper-focused, and comfortably resident in RAM. Hasham sharding, physical split, distributes these partitions across completely independent physical database nodes. A routing tier hashes or maps a shard key, like user ID, to direct the write, not in query, directly to the specific node holding that user's dataset. This breaks the single instance constraint entirely, distributing CPU, memory, and I/O load linearly across a cluster of machines. Cost comparison sharding trades raw compute efficiency for horizontal elastic scalability. It requires higher initial infrastructure spending, but prevents catastrophic exponential cost spikes driven by ultra-high-tier vertical cloud instances. Metric vertically scaled monolith. db.r6g.6x large. Horizontally sharded cluster. 4x db.r6g2x large. Compute profile 64 vCPUs. 512 GB RAM 32 vCPUs. 256 GB RAM. Combined total across 4 instances. Monthly compute cost $7,450. Month $3,725. Month I/O capacity. Performance heavily constrained by single-volume IOPS limits. Quadrupled disk throughput via parallelized independent I/O channels. Operational. Overheard risk of lockups during schema migrations. Complex query routing required. But 0 single points of failure. The financial trade-off. By moving to a horizontally scaled architecture, you cut your raw cloud compute spend by roughly 50% for equivalent performance workloads, because you no longer pay the massive financial premium associated with bleeding-edge, high-end instances. More importantly, you eliminate the looming threat of hitting an absolute scalability ceiling where no larger instance exists to save your system. Actionable fix, PostgreSQL declarative partitioning script. Stop treating massive logs or transactional ledgers as flat fill. Convert your monolithic structure into an automated, time-based partitioned table structure. SQL 1. Create the master parent table, explicitly defining the partition strategy. Create table application Athens. Event ID UUID not null. Tenant ID UUID not null. Event type varchar 64 not null. Payload JSON B. Created at DIXPorps with time zone not null. Primary key. Event ID created. Partition key must be part of the primary key. Partition by linkage. Created 2. Create explicit child partition tables to hold specific time boundaries. Create table application indents. 2026 Q1. Partition of application indents. F4 values from 2026 0101 00 2026 0401 00. Create table. Application indents 2026 Q2. Partition of application indents. 4 values from 2026 041 000 to 2026 0701 003. Verify that partition pruning is actively working via the execution planner. Execute this query and ensure the engine does not scan the 2026 Q1 partition. Explain analyze. Select from application ads. Where created 2026-05-01-00 and created dat 2026-06-01-00. Connection pooling and Layer 7 database proxying the problem. Connection starvation and thread exhaustion. Your application framework is killing your database performance by opening a brand new TCP connection for every single inbound HTTP request, or keeping thousands of idle application threads perpetually bound to database backends. In database systems like PostgreSQL, each client connection spawns an entirely independent, dedicated operating system backend process on the database server. When your traffic spikes, thousands of application containers attempt to spin up concurrent connections. The database server spends more CPU cycles handling OS context switching, managing process locks, and negotiating TLS handshakes than it does executing actual SQL queries. Once you breach the max connotations limit, your database rejects new traffic entirely, throwing fatal too many clients already errors. Your application servers stall, health checks fail, and your entire microservice fleet goes into an unrecoverable death spiral. Engineering, reasoning you must decouple application-level thread execution from physical database connection allocation by injecting an aggressive Layer 7 connection, proxying IR such as PG Bouncer or AWS RDS Proxy App Container Fleet, thousands of ephemeral connections, L7 Proxy PG Bouncer, small, managed pool, production database node. Instead of allowing 5,000 application threads to open 5,000 persistent backend database processes, a proxy maintains a lean, highly optimized pool of, say, 100 permanent physical connections to the database engine. It multiplexes the incoming application requests across this small pool using transaction pooling. The moment an application transaction finishes executing a query, that physical connection is instantly detached from that specific application client and handed to another waiting thread, even while the original client maintains its virtual session with the proxy. This protects your database from memory exhaustion, bounds context switching overhead, and allows your application layer to scale up dynamically to tens of thousands of concurrent tasks without adding a single ounce of weight to your database backend. Cost comparison. Implementing a connection proxy layer vastly reduces the compute specifications required to host your core databases, netting massive cost reductions. Core matrix without proxy layer with dedicated proxy layer RDS proxy required DB instance BDAM6G about 4x large to handle memory overhead of 2,000 connections. DBDAM6G.x large connections bounded to 100. Lower memory pressure. Database compute cost 480 month, 370 month proxy service. Cost 130 month, 0.18 per vCPU hour for proxy endpoints. Combined infrastructure cost 1,480 month, 500 month, the financial trade-off. By deploying an L7 connection proxy, you cut your overall database infrastructure costs by roughly 66%. Instead of paying for a massive, overpowered database instance purely for its memory capacity to hold open idle client connections, you optimize for actual transaction throughput and shift connection management to a highly efficient, lower-cost proxy tier. Actionable fix. AWS RDS proxy configuration via CLI. Force your architecture to route database transactions through a managed proxy endpoint. Here is how to provision an RDS proxy to govern your connection limits. Bash 1. Create the IAM policy allowing the proxy to fetch DB credentials from Secrets Manager. Alice IAM create policy. Policy name RDS proxy secret policy. Policy document. Version 2012-1017 statement. Effect allow action. Secrets Manager secret value resource RNAs. Secrets Manager US East 112345678901112 secret. 2. Provision the DB proxy instance enforcing transaction pooling. AWS RDS create DB proxy. DB proxy name production Postgres proxy engine family PostgreSQL. Auth schemes description production DB. Access secret ARN. Oz, Secrets Manager, US East 1123456789012 secret debcrex xwive, role ARN, Oz AMIA 1234567890112 proxy execution role VPC subnet IDS NUPIT ABC 12345 NUPIT def6789 do require tells. 3. Attach the proxy to your target production database cluster. AWSR register DB proxy target. DB proxy name production Postgres proxy. Target group name default. DB instance identifiers production primary DB. Once executed, grab the returned proxy endpoint URL and force your application configurations to swap out the raw database host address for this proxy endpoint. Set your application-side connection pool limits to burst aggressively into the proxy, knowing the proxy will shield your master database from ever encountering connection starvation again. Premature multi-master write clustering the problem. The high availability mirage and split-brain disasters as system scale, engineering teams frequently fall victim to a seductive architectural mirage. Active-active multi-master write replication. The logic seems bulletproof on the surface. If having one primary database writing data is good, having multiple primary instances across different regions accepting writes simultaneously must be twice as good. Teams rush to implement multi-master clustering to achieve a theoretical zero downtime framework where any node can handle any transactional mutation at any second. This assumption is a catastrophic trap. When you allow simultaneous writes to the same data sets across geographically separated nodes, you are no longer just dealing with a database. You have entered the unforgiving domain of distributed state conflict resolution. Under real-world network conditions, network partitions and variable replication transit latencies are an absolute certainty. When Node A in Virginia and Node B in Dublin modify the exact same row at the exact same millisecond, your database engine is forced to guess which mutation is valid. If your system encounters a temporary cross-oceanic network drop, the cluster can easily fall into a split-brain state. Both nodes assume the other is dead, continue accepting independent writes from local users, and allow their data states to diverge completely. When the network self-heals, you are left with thousands of unresolvable data conflicts, corrupted ledgers, and broken relational foreign keys. Your team will spend agonizing weeks manually writing custom scripts to parse through divergent database state logs, trying to figure out which customer data to permanently delete. Engineering reasoning. The fundamental physics of distributed data systems are governed by the CAP-THAP theorem. You can guarantee consistency, availability, or partition tolerance, but you can only choose two at any given moment. In a distributed multi-master setting, ensuring absolute consistency across continents requires synchronous coordination protocols like two-phase commits, 2PC, or Raft to Paxos consensus state machines, .client app, .renode A, US East 1 synchronous consensus lock, Node B EU Central 1. Block write locally. Block write globally. When you force multiple master nodes to guarantee absolute consistency across thousands of miles, a write operation on Node A cannot complete until it safely secures a distributed network lock from Node B across the ocean. Your write latency instantly skyrockets from 2 mils local NVMe speeds to the 100 milliverse plus physical round-trip time of cross-oceanic fiber lines. If you try to bypass this performance penalty by switching to asynchronous multi-master replication, you trade away your consistency entirely, opening the door to concurrent conflict mutations. The operational overhead of managing conflict-free replicated data types, CRDTs, or resolving last write wins metrics inside a complex transactional business domain introduces severe logic fragility for 99% of applications. The architectural complexity of active-active multi-master systems causes exponentially more downtime and data loss than the simple single primary failure scenarios they were built to avoid. Cost comparison. Multi-master write clusters carry an immense infrastructure premium alongside hidden operational and consulting overhead. Cost category. Single primary with hot standby multi-master, active-active cluster, 2 nodes compute engine licensing 1x, active engine plus 1x, passive standby, 1500 Namo 2x enterprise. SA multi-master engines plus sync modules $3,800 Mocross region consensus egress minimal, heartbeats and unidirectional async shipping, continuous multi-directional synchronous state, sync 450 MOTS Mo operational remediation cost $, automated failover handle, ES infrastructure drops high. Requires dedicated specialized engineering focus to fix data divergence. Total baseline running cost £500 month, $4,250 month, the financial reality. Multi-master systems multiply your baseline infrastructure run rate by a factor of nearly 3 while actively increasing your operational risk profile. You are paying a premium to buy a system that demands highly specialized engineering handling, turning a standard database tier into a highly volatile state mechanism. Actionable fix. Reverting to an active-passive failover pattern. Abandon complex active-active write configurations. Re-architect your system to utilize a strict single primary model backed by a robust, automated active-passive failover topology with synchronous replication, bounded strictly within a low-latency localized region. Terraform Configura highly available. Single primary PostgreSQL cluster with AWS Aurora. Resource always RDS Tezcapel Aurora Python. Cluster Divider Production Core Cluster. Engine Aurora PostgreSQL. Engine Vivation 15.4. Database num Core Brahmanturational. Master U non Cluster Abdon. Master Posits VR.db. Backup retention before 14. Preferred backpike 1102004. Enable storage encryption and automated deletion protection. Storage encrypted true. Deletion protection true. Spin up instance node 1, the designated primary write node. Resource audius RDS clot node 1. Identifier core cluster node 1. Cluster iders EWASP lightider.id. Instance class dbgtox large. Engine Abia RDS tablat Aurora Engench. Engine Vation AWS Arts Koppel. Aurora Augench Favation. Promotion Tier 0 Tier 0 ensures this node is targeted as primary. Spin up instance node 2, the automated failover hot standby node. Resource Audias RDS Clans node 2. Identifier core cluster node 2. Cluster auditor at AWS RDS Cloud Aurora.id. Instance class db.r6g.x large. Performance parity prevents degradation on failover. Engine AWS RDCat Aurora Engench. Engine version download Aurora Triper Engench version. Promotion Tier 1 automatically promoted to primary if node 1 goes dark. The deceptive kill switch. Default storage, auto-scaling, and disk I/O throttling the problem. The invisible silent chokehold. We have arrived at the single most deceptive configuration setting in modern cloud database infrastructure. Unmonitored default storage auto-scaling coupled with credit-based IOPS burst allocations. On paper, cloud storage auto-scaling sounds like an absolute lifesaver. Providers promise that you will never have to worry about provisioning disk space again. When your database fills up, the cloud fabric will silently and seamlessly expand your storage volume in the background. Engineering teams trust this safety net blindly, check the box, and look away. This is a critical mistake that will break your system under load-stored auto-scaling, has a severe architectural limitation that cloud providers bury deep inside their technical documentation, the modification cooldown window. Once a database storage volume undergoes an auto-scaling event, it locks down. The underlying cloud storage subsystem, such as AWS EBS, prevents any further storage modifications or size increases on that volume for a strict 6-hour period. Log spike runaway query, disk fills past 90%, auto-scale triggers. Volume expands. Von locked for 6. Massive data influx continues. Next 30-minute disk hits 100% day-based COSAP. Consider what happens when a rogue application process begins spewing millions of duplicate error logs, or a broken database migration loop starts rapidly consuming disk space. Your database triggers an auto-scaling event, expanding the disk by 10%. But the data influx keeps roaring. Within 30 minutes, those newly added gigabytes are completely consumed. Your database attempts to scale up again, but it hits the 6-hour modification lock. The storage engine can do nothing. Within minutes, your physical disk space hits absolute 100% capacity. The moment a database storage layer hits 100% utilization, the engine enters an unrecoverable failure mode. Transaction logs cannot be written, the engine panics, existing tables risk structural corruption, and the entire database process abruptly crashes. Worse, if you are using standard general-purpose storage volumes, like GP2 or GP3. Running low on storage directly chokes your baseline I/O performance. Your IOPS drop to minimum levels, read queues back up, and your application stalls into total unresponsiveness. You have built a system that actively conceals its own structural exhaustion until it is too late to stop it. Engineering reasoning operating systems and database engines require free disk space to handle complex runtime operations. When executing large queries, sorting datasets that exceed memory limits, or rebuilding indexes, database engines create massive temporary files on disk. If your physical disk usage sits at 95%, a large query requiring a 60 gigabytes temporary disk sort will instantly saturate the remaining storage and crash the entire database process. Furthermore, cloud storage throughput is deeply tied to volume sizing. On basic cloud storage volumes, performance is bound to an allocated credit balance. When your application encounters sustained heavy traffic, it burns through its temporary burst credit pool. If your volume size is too small, your disk performance will be violently throttled down to its low baseline limit. Disk latency spikes from 1 ms to 500 ms. Your database threads lock up waiting for disk I/O, and your entire application tier times out. You cannot trust automated cloud mechanisms to calculate your raw performance limits dynamically during a traffic emergency. Cost comparison relying on reactive autoscaling actually costs significantly more over time than proactively over-provisioning. High-performance storage blocks. Provisioning strategy: reactive autoscaling, small disk plus low baseline IOPS. Proactive over-provisioning, large disk plus dedicated IOPS. Storage allocation starts at 100 GB. GP3, 8-1000 GB. GP3 baseline. IOPS allocation default 3000 IOPS. Throttles under load, 0 provision 12,000 IOPS. Sustained load ceiling, 45,000 MO. Emergency outage, impact high risk of 6-hour lockup crashes. Unbounded cost-stable performance under intense traffic spikes, 0. 0 total predictable cost 8 pints a month. High risk factor 125 pints a month. 0 risk factor. The financial trade-off. Saving $117 a month by skimping on your storage baseline is a terrible trade. By proactively provisioning a massive 1 terabyte storage volume with dedicated guaranteed IOPS, you insulate your business from performance throttling and completely bypass the dangerous 6-hour autoscaling modification lock. Actionable fix: proactive storage allocation and strict alerting. Stop letting your database live hand-to-mouth on storage. Pre-allocate substantial disk space, provision dedicated IOPS independent of disk size, and establish aggressive monitoring metrics to catch storage consumption anomalies long before autoscaling locks you down. Terraform. Provision a rock-solid, high-performance storage layer for production RDS. Resource ADS.BNDISTAS. Production Desker. Identifier: production database secured. Allocated Desker 1000. Proactively provision 1 terabyte. To avoid scaling locks entirely, max DADWELD store 2000. Set an absolute upper safety bound for auto-scaling. Storage type GP3. Explicitly provision throughput and IOPS independent of storage volume size. IOPS 12,000. Throughput 500. Ensure maximum MB second throughput lane availability. Engine: Postgres. Instance class 6 G2X large. Username DBOperator. Password var.dbo. Hestet: create an aggressive CloudWatch alarm to catch disk inflation within minutes. Resource: Oz CloudWatch Miriagalm low.spike panic. Alarm 9 database disk space critical panic. Comparison: Octor. Lestitornum threshold. Evaluation: Barfence 1. Metric name: free storage space. Namespace: AWRDS. Periods: 60. Check every single minute. Statistic: average. Threshold: 10737418240. Alarm triggers immediately if free space drops below 100 gigabytes. Dimensions: DB instance identifier AWS-PureShore-Dastakor.id. Alarm exchange: PagerDuty Tarn. Final warning and the systemic master fix list if you leave your core database architecture configured with default, out-of-the-box cloud templates, your system will eventually fail. Scalability cannot be bolted on as an afterthought when your primary data store is buckling under production load, The settings exposed across this full breakdown are not minor tuning tweaks. They are the fundamental stress points that dictate whether your enterprise platforms survives high concurrency traffic or collapses into an unrecoverable state failure. Take this script, audit your infrastructure state, and enforce these structural fixes immediately. Tastrof Health Matrix and Action Plan Setting feature the default. Risk the engineering target, fix 1. Regional read placement high, cross-oceanic read latency. Single region blast radius, cross-region read replicas for low latency edge data locality. 2. Table architecture, monolithic table bloating, leading to memory-starved B-tree index scans. Declarative partitioning and sharding to keep indexes small and resident in RAM. 3. Connection management, thread exhaustion and server panic via max connection saturation, Lex 7 connection proxying, RDS proxy, PG bouncer with transaction pooling. 4. Right clustering multi-master, split brain state anomalies, and massive network consensus latency. Ontative passive regional topologies with designated failover tiers. 5. Storage management auto-scaling, 6-hour modification.